In the beginning, I wanted to build a desktop 6-axis robotic arm. At the time, I didn't think the technical difficulty of a 6-axis arm was particularly high, but during actual development, I realized that weight and precision were two core issues requiring repeated trade-offs and meticulous design. Beyond that, I believe the most crucial part was actually the control method. While many control solutions exist, I wanted to find one that was more intuitive and human-friendly. Robotic arms on the market, such as brands like Abibi and Yaskawa, mostly lack truly miniaturized products, while some open-source small robotic arm projects can be found on Taobao, and their structures or programs might be similar. In my view, they feel more like scaled-down versions of factory industrial arms, just placed on a desktop. These products are still not friendly enough in terms of compatibility and ease of use, and aren't very convenient to operate. Therefore, I decided to build one myself, to create a robotic arm that could become an extension of the hand. It shouldn't just be a device, but an intelligent partner capable of assisting me with various desktop tasks. I started with the first prototype, but that version reminded me of those bulky industrial products that occupy a lot of desk space, so I kept thinking about how to make it smaller, more user-friendly, and easier to expand. In the end, I chose a solution with a 3D printed main structure. Initially, I considered using all aluminum alloy or other metal materials, but as the project progressed, I found that 3D printing technology is already very mature and fully capable of producing sturdy and lightweight structures. While metal casings are common, they often lead to increased weight and space congestion issues. Therefore, I switched to using basic PLA filament for 3D printing, making the overall structure lighter with fewer parts and achieving higher transmission efficiency. For the transmission structure, I chose a differential mechanism. This structure operates on a simple principle: dual motors work together, which both reduces the power demand on a single motor and provides power compensation. However, the dual motor solution also has wobbling issues due to gear backlash. After multiple design iterations, I nearly eliminated the play by optimizing gear engagement. For the transmission method, I switched from the initial gear drive to a belt drive. Belt drive not only avoids gear backlash issues, but is also easier to maintain. Simply replace the belt or reprint the belt gears. It's low cost and quick. To make the robotic arm control more precise, I added multiple angle sensors, magnetic encoders at the joints. Traditional solutions can only monitor the motor output angle but cannot capture the actual angle at the mechanical end. I placed encoders at key positions, such as for pitch and rotation angle detection, achieving dual closed loop control, simultaneously monitoring both the input and output angles, thereby significantly improving motion accuracy. Building upon the 6-axis design, I added a 7th-axis rail system to expand its working range. For now, to facilitate debugging, the drive belt is not yet installed, but the structure is reserved. Simultaneously, I integrated all electrical components into one device box, resulting in a cleaner appearance and ensuring better heat dissipation. For wiring, I used a cable carrier structure to manage 3 sets of USB data cables, preventing tangling and folding and maintaining tidy and stable operation. For the control method, I completely abandoned the traditional remote control approach and shifted to voice commands and natural language interaction. I hope users can direct the robotic arm to complete tasks through conversation. For example, hand me that tool over there. In the future, it might even assist with computer operations, becoming a true desktop assistant. Currently, I mainly use serial servos, balancing the flexibility of motor mode and servo mode for easier debugging and control. If I have a larger workspace in the future, I plan to use edge computing devices like NVIDIA AGX to control multiple robotic arms simultaneously, enabling collaborative tasks. This robotic arm is still in the debugging and optimization phase, but it can already perform basic point-to-point movements. I hope it can help me solve practical problems like desk clutter and fetching or placing items, becoming a truly practical and intelligent extension tool. The core improvements of the entire project focus on 2 points. 1. Structural aspect, using 3D printed lightweight design combined with differential and belt drive to achieve high-precision dual closed-loop control. 2. Control aspect, abandoning traditional remote control, shifting to voice and natural language interaction, making the robotic arm more aligned with human usage habits. The ultimate goal of the robotic arm is to become a natural, friendly, and efficient partner in people's work. There's still a long way to go, but I'm willing to take it step by step and realize it gradually.